Welcome back, Physics 30. So we've looked at potential energy in the last section and kinetic energy in the section before. Now we look at combining the two of them to find the total mechanical energy. So we look at mechanical energy and its conservation and then problem solving that. So state the law of conservation of mechanical energy and apply that into solving problems. So we can now define a quantity, ET, before you phone home. It stands for total mechanical energy of our system, where it's the sum of the kinetic and potential energies at any moment, and this is referred to as the law of conservation of mechanical energy. So the total mechanical energy in a system is equal to what it has in terms of kinetic energy and what it has in terms of potential combined together. Simple example of the conservation of mechanical energy: neglecting air resistance is allowing a rock to fall due to Earth's gravity from a height above the ground, as shown in the figure you'll see in the bottom right-hand corner. The rock starts from rest. All of the energy is originally potential energy because you're bringing it up from the ground level to the top. So all energy is potential. So if you look down here, so you could write down 100% potential, 0% kinetic at the very top. As the rock falls, the potential energy, which we looked at, EP equals mgh, and recall that when we're lifting something up, it's equal and opposite, or the force applied is equal and opposite to the force downwards. Remember, we use the positive 9.80 meters per second squared rather than doing the vertical F net calculation. We could just assume it's the same. Because the heights, the rock's height above the ground, h decreases as we drop it, but the rock's kinetic energy increases to compensate so that that sum remains constant. So if we look here at our little diagram, as the rock falls, we have a little bit of both. So we have a both, and then right when it hits the ground, all of the energy is kinetic, and at a height of 0, of course, mgh will get 0. So all of the energy is transferred. So that's a key thing to note. When we're lifting something up, it has kinetic and potential energy throughout, except at the very top when it's stopped. And of course, when it's stopped, V is 0, which means EK is going to be 0. So if you look back over here at the top, remember, EK is calculated as 1/2 mv squared. EP is mgh. So when the height is 0, this is 0. So all of the energy must be kinetic at the bottom. Whereas at the top, it's not moving, it's being held there. So V is equal to 0. So EK is 0, and we have all EP. Okay, so over here I just simplified each of these formulas here. So EK is 1/2 mv squared, EP is mgh, so we can simplify it like that. So let's look at that rock example here at the bottom. So if the initial height of a 7 kg rock in the figure on the right is 3 meters, calculate the rock's velocity when it has fallen and it's somewhere over here, 1 meter above the ground. So the key thing here is to look at it. We can figure out the total mechanical energy by looking at what's happening here initially. So initially we have ET equals EK plus EP. So we're told that the rock is held above the ground, so initially that is going to be 0, and all of our energy can be determined by looking at the total potential energy at the starting. Okay, so ET equals EP, which of course is mgh. So we're told it's a 7 kg rock. Again, the force applied to lift it up is equal and opposite to Fg, so I can use positive 9.8. And the maximum height of release is 3.0. So that tells us that the total energy is going to be that. So all the time, ET is going to be 205.8, whether it's at the top or at the bottom or somewhere in between. So then we can look at when 1 meter above So when we're 1.00 meters above the ground, again, use the same relationship. Now this time, 1 meter above the ground, yes, so it's in between these two extremes, at the very top or at the very bottom. So I will have this and I will have this. And so I can break that down into ET equals 1/2 mv squared plus mgh. Now, of course, the total energy, wherever it is 205.8. So at the start, the reason why it was all EP, because at the start, it's held above the ground. It's not moving, so all the energy is potential. So all the total energy can be calculated by figuring out the potential energy at the start. So 205.8, 1/2 times the mass. And we're looking for V squared. Can we squeeze this in? And it's 1 meter above the ground. Just barely able to squeeze that in. 205.8. Half of 7 is 3.5. 7 times 9.8 times 1, 68.6. Subtract 68.6 from each side. And I get 137.2 equals that. And then I'll skip a couple of steps here because I'm running out of room. So divide each side by 3.5. And of course, we have to take the square root of each side. So therefore, V equals 6.26 meters per second. All right, so that's how you handle that with the energy transformation. So again, the key thing here is figuring out the energy at the start, and you're given some information. A lot of times it's going to be lifting something up, and at the maximum height, that potential energy is where 100% of the energy can be found. So on the next page, the total mechanical energy equation can be applied to any object moving without friction under the action of gravity. For example, the figure below, we'll talk about a roller coaster example here. And yeah, we're assuming that there's no friction. We're kind of simplifying it a little bit. Not super realistic, but it makes it a little bit easier to handle. We ignore rotational motion as well, the car's wheels, and treat the car. We can think of it as a particle that's undergoing a simple translation. Initially, the car has only potential energy, because if you've ever ridden a roller coaster, the first part of the roller coaster ride is going to the very top of the roller coaster, right? And then all the energy will be 100% potential energy at the start, and then 0%. Let's make this, use the same symbols here. 100% EP, 0% EK. Because at the very start of the roller coaster, which is kind of the scariest part, all the anticipation of what's to come, you're not moving at the very top part of the hill, and then you go down, and then at the very bottom you may have 0% EP and 100% EK. So it changes at the very bottom. So as it coasts down the hill, it loses potential energy and gains kinetic energy. And the sum of the two remains constant, ET, total mechanical energy. At the bottom of the hill, it has maximum kinetic energy. As it climbs back up, again, the kinetic goes back into potential. When the car comes to rest again at the same height, all of its energy is potential energy. Okay, so key things. The transition from EP to EK and vice versa, but the key thing there, the sum of the two remains constant at total mechanical energy. Given that gravitational potential energy is proportional to the vertical height, energy conservation tells us, now again, if we assume friction is negligible, the car comes to rest at an equal height equal to where it originally was. Now, of course, in real life, that's not going to happen. And of course, if any of you had Hot Wheels tracks as a kid, if you arranged it like this and made a U-type shape, and you had your car, ideally it should come up to the same height on the opposite side, but of course it doesn't because of friction. So of course what happens is that it goes like this, then down, and eventually just stops like that. But in the absence of friction, it would keep going like that forever. Let's see here. If the two hills are the same height, the car will barely reach the top of the second hill when it stops. The second hill is lower. Not all of the car's kinetic energy will be transferred to potential energy, and the car can continue over the top on the other side. The second hill is higher. The car will reach a maximum height equal to its original height on the first hill, again, in the absence of friction. No matter how steep the hill is, since the potential energy depends only on the vertical height. Okay, I think we'll stop there, and then in the part 2, we'll look at a roller coaster example involving total mechanical energy.